to the summer break. Don't let me stay for too long here. Okay. Nothing special today. Our simple nonlinear circuit. So let's talk about the goals first. What we are going to do today. So the impedance of the capacitor is like this, 1 over j omega c. And impedance of the inductor is j omega L. Okay, you can use these terms as a resistor, as what you did for the linear circuits. Just put in there and do the calculations. And most of the time, it's just a voltage divider calculations for the gains. Because you have a frequency term here, it's just one more variable. So what's going to happen is if you just treat this term as a resistor and do the calculation for the voltage divider, and eventually the gain of the circuit or the voltage divider is going to change when you change the frequency, which becomes a filter, because if you have a different frequency, then give you a different gain. If it's a low pass filter, the high frequency part of it will be attenuated based on the calculation. If it's a low pass filter, then the high frequency component will be what? If it's a low pass filter, for example, low pass filter, so the high frequency part of the signal will be attenuated because at low pass, only low frequency will pass, right? For high pass, so the low frequency part of it will be attenuated as well. Where are the applications? Why do we need a low pass filter? Why? Signal processing. And what are the applications? Could you find out one example in real life, in real world? Mm-hmm. Yeah. Yeah. Mm-hmm. Exactly. So when you are applying that DC coupling on your oscilloscope, if you press DC coupling, are you getting all the signals or on the DC signal or on the AC signal? If you press DC coupling when you are looking at the, remember when you can add a DC offside to the op-amp lab, you did, right? Sometimes you choose DC coupling, sometimes you choose AC coupling. So the AC coupling removes the line, which is the DC part of it, only shows the varying signal, okay? Even though it's not a really, it's probably more complicated than the filter itself. But if you do AC coupling, what's the component is being filtered out? If you press AC coupling. So AC coupling removes the DC offset, right? Okay, so is that a high pass or low pass? High pass, because the AC signal will stay, which is the high frequency part will stay, but the low frequency, which is, what's the frequency of the DC signal? Probably, yeah, it's a very low frequency and it's being filtered out, right? So for the DC coupling, it just allows everything to pass. Okay, and when you see a circuit like this, that's the first circuit you're going to build on the breadboard. I'm going to show you how to build an LT spice as well. That's one of the best ways to run any simulations without put your hands on the breadboard. Sometimes it takes time. So for this one, I can easily tell it's a low pass filter, but why? Exactly. Does everyone else get it here? So this is the voltage. If you treat this one as a Z, as an impedance or a resistor, okay? So the impedance of this resistor is 1 over j omega c. Here, all right? And if you got a high frequency for omega, the overall impedance becomes pretty low because this is omega is in the denominator. So if you got a high frequency and you got a low impedance, right? And this is a voltage divider circuit. You got one resistor, another resistor. If you have a high frequency signal coming from V in, then the impedance of the capacitor becomes very low or high. And why? For high frequency, like one gigahertz, for example. 1 gigahertz, if you put in the denominator, the impedance of the capacitor becomes super low, close to zero. So which means you're shorting the output to the ground, right? So this part is a voltage output. If you short this to ground, there's no voltage drop across these two terminals. So you are getting a super low voltage, which means if you have a high frequency input, and you are getting a really low output amplitude because it's being increasingly attenuated by the filter. Because this point is being shorted to this ground, to the ground here. Okay, so this is a low pass filter because high frequency signal will be shorted to the ground, or we can say the high frequency signal will be attenuated by this filter. If you look at this one, second one, I don't have to ask because you know the first one is low pass, this one must be high pass. But why is that? High pass, right? For low frequency signal, for example, like DC signal won't be able to get through this capacitor. It's only accumulating these electric field, the charges on the two plates of the capacitors. Nothing can get through for DC. It's an open circuit. So DC signal will be attenuated because it won't be able to pass. But for AC signal, it will be able to pass because AC signal comes in. If you look at the impedance of the capacitor, the resistance of this one becomes lower compared to the if you got a DC signal for it. Okay, so eventually this becomes a finite resistor that it can pass your AC signal across this capacitor. But how that works, it seems like magical, right? You got an open circuit, but AC signal can pass. What's really happening there? Yeah, it's actually pull and pushing the charges in and out into the plates. So if you have charges getting in and out from the one side of the plates, it's going to affect the other side as well because of the electric field. So nothing physically gets through, but it's just affecting the charges coming in and out through the electric field. Make sense? Okay. So how to do the calculations? Like the gain, right? How much it's going to attenuate the signal, and also how much phase shift is going to happen from the input to the output. For the first one, let's run the simulation first, okay? Run the simulation first. More fun here. Calculations are so boring. Are these the values I'm going to use in the lab? 1K ohms, right? 1K ohms, 0.1 microfarads, and 5 volts VPP. And definitely we can build a circuit in LT spice. 5 volts. I think this makes it like 10 volts VPP, so I have to change it. 0.5. 1K, 0.1 microfarads. So whatever I'm doing here is translatable to your oscilloscope. It's very similar view compared to your oscilloscope. So what I'm going to do here, like for example, I'm measuring the phase shift of the two signals, input and output. You'll do the same. Just activate your cursor on the oscilloscope and measure the time difference, the delta t over there, and calculate your phase shift in terms of angles using a certain equation on the instruction. So this is circuit, and I will label it really easily here, like V in, and I'm going to do V out. That's the output. The transient analysis for 10 milliseconds, because the period of the sound wave is 1 millisecond. If do 10 millisecond simulation, I'm expecting 10 periods in the monitor. That's the input, that's the output. So it's being attenuated because this is a low high pass filter. Is this a low or high pass? Wait. Low pass, right? There's no capacitor to block the DC signal. You got a DC, it's going to pass the resistor and reach the VL. So there's no way to block the DC. However, if you have a high frequency, it's going to short VL to ground through the capacitor. So it's a low pass filter. So for high frequency, it's going to be attenuated by the filter. So what's the next step? Assuming this is your oscilloscope. So activate two cursors, measure one, and measure the other one. Because that signal is given. So the input comes from the function generator, so you don't have to measure it. You know what's going on. It's going to be 5 volts VPP, okay? Then you just want to measure your output. So I should activate the output cursor, double click in LTSpice. I have two cursors in on the oscilloscope we can press. Just press it and then it's going to activate two cursors. So if you zoom in here, I'm targeting the output, which is a kind of purple color trace. Blue color probably. And here's a reading, and you can see the very similar reading on our oscilloscope. So which are looking at right now. Which are supposed to look at. Huh? So I put my cursor here, right? Is that VPP? I put one at the P, and the peak here and the bottom here, right? I'm trying to measure the VPP of the output. So I'm getting VL, amplitude. So I should read what? Delta V, right? It should be delta vertical. That's a difference. Cursor 2 minus cursor 1, but vertical. So that's a vertical difference, which is reading the VPP of the output. So definitely it's attenuated. I have a 5 volts input, but now I'm only getting like 4.2 for the output. So the voltage or the signal is being attenuated. So you measure it and put it into you open up the Excel sheet and put in the Excel sheet for a certain frequency, right? Because if you look at the lab menu, it's asking you to measure the output voltage at all the different frequencies, 10 hertz, 20 hertz, 5 hertz, for all of them, and plot it, okay? So this is a frequency for each test. I only tested what here? 1 kHz, okay? Now you move to the next data point, you change the frequency of the function generator and change it to 10, for example, and rerun it. I have to change the simulation time in LTSpice, but you are not doing LTSpice. And for 10 hertz, I'm going to run, for example, let's do 1 second. Should be adequate for that. Where's the output? They're overlapping, no? Why? Because the frequency is pretty low, so almost everything passed through the, so pretty much nothing is getting attenuated and shifted. But still want to measure it to report the results. You click it twice in LTSpice, targeting the peak-to-peak voltage, and eventually you can measure that, which is like 4.9 or something. So it's not almost not being attenuated at all for low frequency, which makes sense. This is a low pass filter. For low frequency, it shouldn't be attenuated too much. And you keep doing that and change it to, you have to follow the instruction to use all the data points is being suggested in the menu, but I'm going to pick up another one, for example, 10K, and I'm going to use 1 millisecond for the simulation time. I'm going to plot it again. You can see the signal is getting lower, okay? Only 0.7 millivolts, 0.7 volts or 700 millivolts, okay? Just do all the data points to finish, I think that's number 1. The first task you have to do, okay? That's the first one you have to do. And what about the second one? It's going to be the phase shift. How to get the phase shift over here? Still, you have to do all the data points, all the frequency points, and plug in all the time differences you measured on an oscilloscope and report it to the Excel sheet before you plot it. So now, for example, I'm trying to measure the 10K hertz. So how to measure the time difference? Delta X, yes. So I activate one cursor and find out another cursor, targeting the 2 peaks. And now I can measure the horizontal difference, which is 22.7 microseconds. That's the delta T. And you do it for every single frequency and put in the Excel sheet. Okay. Very similar for the high pass filter. It just swap the positions of the resistor and capacitor in the circuit on your breadboard and do the measurement. Okay. So now let's go through the calculations. Which is the theory behind running behind the scene. How that works. As the input signal, it's a sine wave. We've got resistor and capacitor here, and ground. That's R, that's C, that's V, that's VL. All right, if you treat this one as a resistor, so the impedance is 1 over j omega C. So VL, according to the voltage divider theory, VL over V in equals 1 over j omega C over R plus 1 over j omega C. No problem here by far, right? And this equals, if you times j omega C on the top and bottom at the same time, you're getting 1 over 1 plus j omega RC, right? And then find out the absolute value of this guy, VO over VI. This is 1 over 1 plus j omega RC, which is 1 over. Did you learn how to get the absolute value from this one, from the imaginary number? Have you learned it? 1 plus, yeah, 1 plus, yeah, modulars, how to pronounce it? So that's a complex plane, right? We got a 1 here, and that's a J plane, a J axis. So 1 is here, here is omega RC. That's on the unit circle. This actually should be, I didn't draw it correctly. Do the circle first. Okay, here's omega RC, and this is 1. So what's the amplitude of this signal? J plane. So it means this line, right? Which is 1 square plus omega RC square and square root of it. Okay, so if you have this one derived, you can actually find out the attenuation of the amplitude or the gain. It's not actually gaining anything, it's just attenuation. So VO over VI is VL over VE. Okay. If we plug in, so R here is 1 k ohms. This is 0.1 microfarads. You plug in these values into this equation, I can find out what is VO over VI. Since VI is given, you know it's 5 volts. So you can calculate for VL from this equation. And I think the final result is 1 over 1.18, which is 0.847. That's V over VI, okay? If you use this one times 5 volts, you can get VL. And what is that? Somewhere like 4 point something volts, right? 0.847 times 5 volts, 4.235. That is the VL you are supposed to get. And now we come back to here. And the frequency is 1K instead of 10K. And now let's verify it, see if that works as we expected. So we are expecting 4.235 volts for the output. And now let's measure it. I'm pointing to the peak and then to the bottom peak. And that's very close to the theoretical result. Any questions by far? Am I missing anyone? So now I think just to follow, instead of thinking about like why we have to do that, just follow the calculations. You are not doing a verification, I don't think so. For the lab, you just build everything on the breadboard and change the frequency and plot it. And log the data to the Excel sheet and plot it eventually. But I need to know some of the calculations for maybe the very last one, so know what's going on, okay? So this is the amplitude. What about the phase? The phase change. I just showed you how to measure the phase change on the oscilloscope. For example, you are pointing to here, to the input, and then you point to the peak of the output, so you can look at the delta T, which is this one. So that's delta T. And if you look at the instruction manual here, if you got delta T, you time the frequency, which is the frequency you set up, right? And times 360 degrees, you are getting the phase shift, feet here. So this one will be in degrees. Why it works that way? So this is the same thing as delta T over the period times 360 degree, right? So this will be easier to understand. I told you this is boring, you don't believe me, but now looking at your poker face, I know it's boring. Oh, no, I'm really tired. I know, everyone is tired. Okay. Yeah. So phi is the phase shift, it's in degrees. You can definitely, when you are measuring the difference on the oscilloscope, is that time or degrees you can measure? It's gonna be time, okay? So I have to plug into this equation and find out the degrees. All right? How to get the degrees? The time, the delta T, over the period. So also you can treat this guy as a 1 over the period, which is the frequency, is the same thing. All right? This is easier to understand. So the delta T the portion of the delta t in the whole period, which is equivalent to the portion of it in the 360 degrees. You know what I mean? So you can convert that delta t into the degree counterpart of it. Make sense? So this equation makes sense, right? Okay. So what you are going to do? When you are measuring that delta t on the oscilloscope, you got that data, you plug into this equation and find out the degrees. And put it into the Excel sheet as another column and be ready to plot it later. What's the input? No. Frequency. That's your input. See, there are so many points. The goal, I think the reason that if Jason gave you so many points over here is the x-axis is frequency. So you have the x-axis at the input, you put into different frequencies from the function generator, and then you measure the attenuation of the amplitude and also the delta t of the signals. So you can have something on the in the Excel sheet is like frequency and amplitude and delta t. And if you put an equation in the Excel sheet, it's going to do all the calculation at once, right? You don't have to manually calculate it. Delta phi, which is this guy, right? All the columns, just put in Excel sheet, plug in all the frequencies here, measure it, get the amplitudes, and measure it, get the delta t, and calculate it, get a delta phi here. Same for this one. Change the circuit, exact the same process. Super fun. Do it. No, I will get another one, the final one. I haven't gone through all the calculations yet. Don't want to make you guys asleep. All right. High pass. Wait, how do you calculate the angle difference here? The phase shift in theory. How to calculate the phase shift? We just calculate the amplitude and we verified it, right? But how to calculate the phase shift in theory? It's basically just the time difference between the output and the input. And you have this equation here, or here, as the transfer function of it, right? And the top is equivalent to 1 plus J0 because there's no imaginary part of it. So just put a 0 here, so 0 times J. So the angle of this guy is arc tangent 0/1. That's the angle for this guy. Why? Because if you are looking at the unit circle here, right? So the J part, the imaginary part is here, and that's a real part. So the angle here is arctangent of this divided by this. Okay? So now this is the imaginary part, this is the real part, so it's going to be 0/1 arctangent, which will be the angle here. And that's the output, and you have to minus the input to get the time shift. So the input is this one, which is arc tangent j omega c, omega rc, sorry, over 1. And this is 0 degree minus. If you plug in all the numbers in there, you use a calculator online, I can find out this one equals 32.13 degrees. And so eventually you are getting minus 3.213 degrees. If you see a minus sign here, which means it's delay. the lane. Okay. That's how I calculate the phase shift in theory. That's a low pass filter. What about high pass filter? It looks slightly different. 1 over j omega c, it's R, it's a VL, this is V in. So VL over V in equals R over, that's the output stage, R plus 1 over j omega c. And times j omega c on the top and bottom, you're getting j omega rc over 1 plus j omega rc. And you know that the real part of this, of the numerator is 0, right? So for the amplitude, it's not affecting anything. It's just V over VI. For the absolute value of it, you're getting omega RC on the top, because that's 0 squared plus omega RC square root of it is still omega RC, no difference. It's like this, right? And the bottom becomes 1 square plus omega RC square, which is omega RC over 1 plus omega RC square root. That's the amplitude change. If you do the calculation and run the simulation, it's going to match. But the lab is not asking you to do the calculation, just let you know how it looks like. Is this what you are, if you are trying to match the theory and the measurement, you have to do this calculation to find out the amplitude attenuation. What about phase? It's just the angle of VL minus the angle of the time difference, which is minus. You use the subtraction to find out the time differences. So on the top, what's the angle of it? Arc, tangent, omega RC over 0. That looks odd. Minus arc, tangent, omega RC over 1, right? So what is this? So if you look at the triangle, whenever it's super slim like that, if you keep moving this line up, that in that direction, eventually at the point, they are going to overlap, getting very close to each other, right? This is 90 degrees. We are moving them very closer and closer. This one, so this becomes the imaginary part of it, which is omega RC, for example, and this one is getting squeezed. Eventually becomes 0, which is the denominator here. So what's the degree here right now? Did they teach you that way when you are learning this? Like tangent 90 degrees, and so what is tangent 90 degrees? Do you have that? Like, for example, this is AB, right? A over B is tangent theta, right? Make sense? You learned this, right? Okay. So this is definitely not less. This is definitely less than smaller than 90 degrees. So what about whenever this angle here becomes 90 degrees? What's going to happen? This triangle becomes super tall, right? Like keep squeezing together until it becomes like super small at the bottom. For the bottom edge here, becomes super short or small, and becomes a super high triangle like that. Whenever it's getting closer to 90 degrees. Okay. Then this one becomes 0, very close to 0, you know, approaching 0, which is this situation. So what is this angle here? If denominator is 0, what's the angle? 90. Minus what? Whatever it is, right? Calculate it. And you finally find out the degree here. Make sense? That's how calculate the phase shift for high pass filter. And there's another thing you have to do, which is the very last one, the 3 dB frequency attenuation. It's very confusing. Did you learn in the class? 3 dB frequency of the filter. Did you learn it in class? No. A Bode plot, yeah. So Bode plot is the one I showed you. Here. So we got a frequency in Excel sheet, right? You are trying to plot it. So the x-axis is the frequency. You got 10 hertz, 100 hertz, 1K, 10K, 100K, for example. Okay. And for the amplitude, instead of using, so for here, right, we're not using VL. No. We're not using VL over VI. Nope. We're using 20 times log base 10 amplitude as absolute value of VL over VI. That's what we use. Why do we use 20 times log instead of using this one, the linear one? That's right, yeah. So you can put all the data in one plot instead of extending it all the different places. So we use 20 times log for the y-axis, V over VI in the inside, right? And x-axis is F, is the frequency, and that's Bode plot. Yeah. Exactly. It's called decade, 10 times. But they linearize decades. Yep. So if you have 20 log VL over VI, and which is like there's no attenuation, for example, so this is 1. And what is that? No attenuation, VL over VI. No attenuation. Are you getting amplification? Is that possible to get amplification? It's not amplifier, right? If you get amplification, why do you need an op-amp? No amplification, never get any amplification. So the maximum value you can get is the original value. So not being filtered, not being attenuated, which is the lucky part of it. And so if there's no attenuation at all, for example, so this equals 1, right? So what is the result? 0. And the unit is dB. So the unit of 20 log, whatever result you're getting is dB, right? So if you have no attenuation, it's at 0 dB, 0 dB for the plot. So at the very beginning, for low pass filter, okay, this is a low pass filter, okay, this one. For frequency 0, like DC output, 0 hertz DC, right? How much dB? Low pass filter, 0 dB. Why? No gain, no attenuation, 0 dB, because V out over V in is 1 for low frequency, no attenuation, DC voltage, and you are getting 0 dB. That's going to last for a while. You couldn't visualize the difference. Actually, it's falling but very small range, like this. Whenever you are getting higher frequencies, attenuating the signal. So VL over VI becomes lower. It's going to be smaller than 1. So the final result will be lower than 0 dB. Does that make sense? So when can you get 3 dB frequency? If you look at the instruction, it's asking you to find out the 3 dB frequency on the plots. So I have to find out 3 dB. How can I get 3 dB? The highest is 0 dB. Where's the 3 dB? Keep in mind, 3 dB frequency is actually minus 3 dB frequency. It's over here. So when 20 times log V over VI is minus 3 dB, you'll find out the plot here and try to locate that frequency, find out what's the frequency. It's giving you a minus 3 dB attenuation. So the reason we use that one is because we consider the minus 3 dB is still not a significant attenuation. We consider all the frequencies here is passing through the filter, not getting attenuated significantly. That's the boundary of signal being filtered, signal being maintained, not being kept, not being filtered, but attenuated. All right. So how to find out the 3 dB frequency? In your measurement, how to find it? Do we have a frequency domain? No, it's just time. You got sound waves, right? So when you measure, you have to know when you are reaching 3 dB. So it's actually 20 log something over V over VI, which equals minus 3 dB, right? And you move 20 over here, you're getting log V over VI equals minus 3 over 20. All right. You have to calculate what is this guy is. It's a minus something, right? And then use the calculator to find out what is V over VI from this. So this becomes 0.707 or something. Okay. So when you have your input and output showing displayed on the oscilloscope, use the knob of the frequency of the function generator. Use the knob. Don't try to put all the frequencies over there when you are doing the last one. But for the previous ones, definitely you need the exact frequencies at the input signal, for the input signal, one by one. But for the very last one, when you are you are doing that in the opposite way, right? We are trying to find out the frequency that giving the signal a minus 3 dB attenuation. Okay, for this specific task, what you are going to do is start with a very low frequency, so there's no attenuation. And then you keep changing the frequency through the knob on the function generator until you see a 0.707 output. You know what I mean? When you are increasing the frequency using the knob of the function generator, the frequency is going to go up, right? And then you are looking at the sine wave. The cursor keep measuring that sine wave until you see a 0.707 attenuation. You stop at that frequency. So you know that frequency will be the minus 3 dB frequency. Why we want to see that? Why do we want to know that? When the signal will be attenuated, or at which frequency the signal will be attenuated. It's called a cutoff frequency. So when you are trying to characterize your circuit, you want to know the bandwidth of it. So the 3 dB is actually providing you the bandwidth. For the low pass filter, if you find out the 3 dB frequency, right, you get attenuation first and locate it on the curve and find out the X value of it, which is a frequency. So that's your bandwidth of the circuit. or you can say that's a pass band of the circuit of the filter. That's a bandwidth. Any frequency higher than the bandwidth of it will be attenuated, it won't pass the filter. I've heard about the bandwidth term a lot of times, right? So here it comes. That's the bandwidth of the circuit, of the filter. Cutoff frequency, which is here. Okay? Any questions by far? Deeper slope, you mean steeper? Yeah, higher order of filters. So adding more caps and resistors in here. Or use the active filter, adding op amps in there will help as well. There are a lot of things about filter design. Do you know what you want to do, what you are supposed to do for the lab? Is that clear? Are you going to do? No. Open up the spreadsheet and start plugging numbers in there when you are changing the frequencies. Yes, yeah. It's just 2 tabs in one sheet. But you need to do the same thing for the two types of filters.